one thing that we'll often want to do in applications is find an exponential function that goes through some data points. And there are really two ways to go about this. So for an example, let's find the exponential function through these two data points. Now the two ways of doing this correspond to the two ways of writing exponential functions. So one way of writing an exponential function is some constant times a base to the x, and another way of writing an exponential function is some constant times e to the kx, and here k is some constant. You can always go from one to the other because if k is the natural log of b, then a times kx, so if k is natural log b, then we can write this as a times e to the natural log b to the x, but then e to the natural log b is just b, so b to the x. So you can see you can always go from one to the other. And really it's just a matter of sort of taste or which you choose, or sometimes in some applications one of these will be more convenient or more common. In many engineering and science contexts, it's common to just always use an exponential written with e like this. But sometimes having your base explicitly written down is nicer. It really depends on the situation. So let's see how we can use these two data points to find the exponential function, or the formula for the exponential function. So let's use the one on the left to start with. Anytime you have data points and you have a form for a function in mind, or a type of formula, you can always get equations for the unknown constants. Right here, x is the variable. We need to find a and we need to find b. We can always get equations to solve if we just plug in these data points. So if we plug in the first data point, 1 and 1/6, we get, let's see, the output is 1/6, and then the x value is 1. So this is a times b to the first. I do the same thing for our second point, and we get 3 equals a times b to the third. Now for exponentials like this, there's a really nice way to make progress in solving this system. You can see in general you're going to get these clumsy exponents on b, which can make it kind of messy to explicitly solve for b. But one nice way of doing it is just dividing these two equations. So we can do 1/6 divided by 3, and that's 1/18. And then on the right-hand side, we can do a times b to the first divided by a times b cubed. So a times b to the first over a times b cubed. And then the b's, see, what happens here is, this always happens for this exponential formula, the a's will simplify away, and then b over b cubed, that's 1/b squared. So 1/b squared is 1/18, and this means 18 is b squared, and this means b is the square root of 18, which is going to be, I guess, 3√2. All right, so now we know b. Now we can go back to one of these two equations and find a. Let's use this one here. So 1/6 is equal to a times b, which we now know is 3√2. And then divide both sides by 3√2. You get a is 1/18√2. All right, and now we know a and b, so we can use these to write down the formula for our function. So f of x is a, which is 1/18√2, times b to the x, and b is 3√2 to the x. Okay, so there's our function. And you can see it's written in the form a times a base to the x. Now if you need to fit an exponential to a couple data points and you want to use this flavor of the formula for an exponential, you can plug in these data points just like we did before. The equations you get will be a little different. So we get 1/6 equals ae to the k times 1, so just ae to the k, and then when we plug in our second data point, we get 3 equals ae to the 3k. All right. Now how we make progress on solving for k is similar. We divide these two. So this time I'm going to do the second one divided by the first one. So 3 divided by a sixth is 18. And then ae to the 3k divided by ae to the k. This simplifies to ae to the 2k. Okay, now we're solving an equation for k, and we're going to have to use a logarithm. So, you know, for this particular example, we got exact results using this first method. If you're going to use this ae to the kx version of an exponential, you're kind of committing to using decimal approximations. In many contexts, that's no problem, but you know, since you're going to end up using a logarithm, you're usually going to end up with messy results if you try to keep things in exact form. So you're kind of accepting decimal approximations at this point. Okay, so let's take a natural log. We get natural log 18 is 2k. And so k is 1/2 times the natural log of 18. And you can see at this point, you'll probably be tempted to get decimal approximations just because carrying around natural log of 18 is kind of annoying. So 1/2 times natural log of 18 is about 1.445. We'll call that good. And then we need to use one of these original equations to find a, so let's use this one. 1/6 is a times e to the 1.445. So a is 1/6 times e to the 1.445. And then we can get a decimal approximation for this. 1 divided by 6 times e to the 1.445. Careful with my parentheses. I get 0.03929. And so the function is 0.03929 times e to the 1.445 x. Oh, this is f of x. Okay. Now, if we actually punch this into a calculator, 1/18√2, it actually would give us this number here. And if we calculated e to the 1.445, that actually is going to be 3√2. So these functions are really the same. They just look different because here we got decimal approximations, and here we used exact forms.